Yes.
help speed up reactions in our body?
Yes. These are organic catalysts, which speed up the rate of reaction without getting altered themselves. Okay, move on.
Biological catalyst.
Yes. Okay. Which solid catalyst will speed up the decomposition of hydrogen peroxide?
Manganese oxide.
Manganese 4 oxide. Manganese 4 oxide. What's the formula for manganese 4 oxide?
MnO2.
Very good. And why is it MnO2? Why is it MnO2? Can anybody explain me real quick? Did you remember how to write the formula? Come on. Why is it MnO2? Muhammad, Sarah, Hamza. Okay, real quick. Mn, manganese 4 oxide, right? It's manganese 4 oxide. So why is the formula MnO2? Is because this 4 is telling us that the oxidation state of manganese is +4. Why +4? Because this is a metal, so it's going to give away the electrons, so it gets a positive charge on itself. Oxide is an anion, -2. Oxygen is in the 6th group. And so we write the oxidation states crisscross. We crisscross, you will write the oxidation state of manganese here, of oxygen here, and they get cancelled. Yes, the oxidation states get cancelled. Okay, if there are multiples of the same number, they get cancelled. So we get MnO2. Okay. Okay, that's why the formula is MnO2. You should know this. Why is the formula MnO2 when it is manganese 4 oxide? Okay, so I hope you now know. If anybody wants to ask any question, if anybody does not know how to do this, please let me know. By the way, I have covered this, how to write formulae, and the video is in my channel as well. Okay. Next question. What are the catalysts in? Okay, we have not discussed Haber's process and contact process, so I will skip this question. Okay, when we will cover them, then we will deal with these questions. Okay, 7.14. What changes in physical conditions are enzymes particularly sensitive to? Yes, very good. Ajwa?
pH.
Yeah.
Temperature and pH.
Okay, what did you say? pH and?
Temperature.
Temperature.
Yes, okay, temperature and pH. Okay, next question. Does the presence of a catalyst increase or decrease the activation energy for a reaction? First of all, what? Yes, yeah, please answer when I say your name, only then you answer. First of all, tell me what is an activation energy?
May I?
Yes, Nabil.
The energy used to start up a reaction.
The energy required to start. Yes. Okay. Yes, the energy that the molecules must have, the least amount of energy that the molecules must have before they collide in order to form the product. But yes, the definition that you have given is also correct. The energy required to start up any reaction. Okay. Okay, so now, does the presence of a catalyst increase or decrease the activation energy for a reaction? Sarah?
It decreases the activation energy, so it is easier for them to react. And they will need less energy.
Yes. Okay. It's easier for the reactant molecules to react. Okay. Next question. In terms of the collision theory, explain why the rate of a reaction increases with an increase in temperature. So briefly, using the kinetic theory of matter, briefly in 1 or 2 sentences, please tell me how does, okay, Sidra wants to say.
So when you increase the temperature, you are providing more kinetic energy to the molecules.
Loudly, loudly.
You're providing more kinetic energy to the molecules, and so they will collide with more force, and there will be more chance of a product being produced.
Yes, so their average kinetic energy should be greater than the activation energy before collision or at the time of collision, so that their collision is fruitful and it results in a product. Okay. B, an increase in the surface area of a solid reactant. Increase in the surface area. Yes, Sarah?
There are more atoms exposed to the other gas, or if the other reactant is gas or liquid, more atoms are exposed, and so more atoms would react in a given time.
Okay, yes, you have the idea, but my only the only thing that the only problem that I saw in your answer was that you were using the term atoms. Don't use the word atoms. It is the ions, or mostly it is the ions, or you can say the reactant particles. You can use the term atom, but then say reacting atoms. Okay, but ion is a better term. Ions or reactants or reactant particles. Well, if you are using the term reactant, then it's okay if you use the word atom. So yes, because more reactant particles are exposed to each other, therefore the frequency of their collisions will increase, and therefore more collisions, therefore more product formed. Okay. C, an increased concentration of a reacting solution. Yes, Nabil? Yes, Nabil?
The collision increases.
Is that it? Yeah, okay. An increased concentration. Can you please elaborate a little more? First of all, say something about concentration. What is concentration? What do you understand by concentration? Concentration is? Come on, Nabil, you're correct.
The amount the water is less.
The amount of?
The amount of the reactant or the substance is more than the water.
No. You will say no. Concentration is the number of see, it is the amount of reactant, or it is the amount of the substance per unit volume of the solution. Okay, it is the amount of substance per unit volume of the solution. That is the definition of concentration. So if concentration, I can write it like this. Amount of substance, what do you mean by amount of substance? It can be mass, it can be number of moles. It depends upon what you are dealing with. Amount of substance divided by the volume per unit volume of solution. Okay, so this is concentration. So when concentration increases, what does that mean? That means you have increased amount of substance in the same volume, or maybe less volume, but this cannot increase. If this increases, the concentration would decrease, right? So if the concentration is increasing, that means it is either same, either it is constant, or it is decreasing. So now you have more. For example, this is your unit volume. For example, this is the unit volume. For example, this is 1 cm cube. Okay, initially you had 3 particles. Okay, now you increase the concentration. What happened? In the same unit volume, now you have more. Okay, you have lots of the same particle. Now, are the chances of collision greater here or here? Of course here, right? The chances of reaction, the collision, meaning they will collide with each other to form the product, the chances are greater here. Okay, the chances are greater here, so the rate of reaction will be greater in this case. This is increased concentration. So that's why when you have increased concentration, that means you have greater number of particles in the same unit volume or in a smaller volume, which means that the molecules are closer together with less space in between them, and so their chances of colliding with each other are more, and therefore the chances of making the product is more, and therefore the rate of reaction is greater. Okay, so this is how increased concentration would increase the rate of reaction. Okay, okay. Next question. Okay, so these questions I have discussed with you. Okay, Now let's move on to the end of chapter questions. Okay. Sometimes in chemical factories, runaway reactions occur. These are reactions which begin to take place much too quickly and can cause explosions, which are very dangerous. In what ways can reactions be slowed down?
By decreasing the surface area?
Very good,
I
Ibrahim.
mean increasing. I mean increasing.
Yeah, decreasing, right? So what you will do is, what they are asking you the ways to slow down reactions, right? And in the chapter you have read about the ways to speed up the reactions, right? So just go reverse. Okay, whatever factors, so those are the same factors which affect the rate of a reaction. So you know that how they speed up the reaction, the same if you take them the opposite way, can slow down the reaction. So yes, one way is to decrease the surface area. And how will you do that? By not using powdered form, but in fact using them in big clumps. It depends upon what reactant you're talking about. If your reactants are gases, then of course surface area, I don't know, surface area won't be effective. Yeah, you can Sisita, you can speak up, please
You
speak up.
can decrease the concentration.
Yeah, we can decrease the concentration if our reactants are in the solution form, right? And if they are gases, then what can we do?
We can bring them closer together.
Zor se bolo beta.
We can bring them closer together
Yeah, you want to bring them closer together, and how do we do that?
by either cooling it.
Yeah, well, if you will cool them, then they will not have enough kinetic energy. They won't have activation energy, so you cannot bring them
So
closer
you can
together.
apply pressure.
Yes, pressure. We will increase the pressure. By increasing the pressure, we will bring the molecules closer together. Okay. So in case of gases, I mean, of course, we cannot make them more concentrated by, like they are not in the form of solid in solvent sort of situation. For example, this is a compartment and it has 5 molecules. Okay. Now, if I want to bring them close together, the only way I can do that is I use a smaller container, same mass. I have same 5 particles, but I decrease the volume. So again, it's like, number of particles per unit volume. This is, but we don't use the term concentration for gas. We don't use the term concentration for gases. We don't use concentration. We use, I forgot.
Moles.
No, I totally forgot. It slipped my mind. What do we use? Yeah, we use partial pressure. Yes, so you haven't done well. That's A level, so forget that. But just remember that concentration is a term which is used for gases. Why? Because remember, concentration definition is this: amount of substance divided by the volume of solution. Now gases are not in that solution thing. Okay, so that is why we use pressure. So what is this? What is this? This is pressurizing. I increase the pressure of the gas. I squeezed the gas into a small volume, so it's the same like I pressurized them. Okay, so we can increase the pressure of the, we can decrease the pressure of the gas if we want to slow down. We can decrease the concentration if the reactants are in the solution form. Then yes, as Ibrahim said, we can decrease the surface area by, don't use powdered form, use big chunks. And what else? We can decrease the temperature, right? What else? What were the other factors that were affecting? Yes, Hamza?
Remove any catalyst.
Very good. Yes. If there is any catalyst being used, remove it. No need for catalyst. Any other? Was there, are we missing on any, okay. So yeah, you can have a number of answers here. Let's move on to question number 2. Yes, please. Sidra has a question.
I'm saying that if you
Loudly.
I'm saying that if you decrease the pressure and you bring them together, they will still have the same energy. You're not decreasing the energy.
No. You're increasing the pressure, not decreasing.
Yeah, so you're increasing the pressure, but you're just bringing them closer together. You're not decreasing the temperature to slow them down. Or anything.
No, because well, it depends upon what the activation energy is of the reaction. So I mean, even if you are decreasing the energy, it should not be below the activation energy. Okay, yeah, okay. Question number 2. When iron 2 sulfate crystals are heated in a test tube, they change to a white powder and condensation collects at the top of the tube. This is the equation. Write a word equation for the reaction. So what would be the word equation? Anybody wants to do this? 2 part A. You guys have done these questions, right? In school. Come on. This is easy. Can you see the book in the camera clearly? Can you see the book?
Blurry.
Yes, miss, it's blurry.
It's blurry. Okay. Oh, do you have the books, right?
Yes.
Yes, may I try?
Yes, please. Yes, Nabil.
Hydrated iron sulfate gives
Oh.
us, when heated, iron sulfate and water.
Gives us what? Water and
Iron sulfate.
okay, just iron sulfate and water. Is that the answer? Is it better now? Is the picture better now?
Yes, it is.
Okay. So yes, Nabil, your answer is pretty much correct. Yes. But I am repeating your answer. Make sure that did I get your answer correctly? ये नहीं इससे लाइनें आती हैं इससे मुझे ना लाइनें आती हैं ये क्या मसला हाँ okay, write a word equation for the reaction. So we have hydrated iron 2 sulfate. That's correct. It's okay, leave it. This is better now. And water, and this will be called anhydrous. Anhydrous meaning without water. It is the opposite of hydrated. So I will write it like this. This will be my word equation. Hydrated iron 2 sulfate will give us anhydrous iron 2 sulfate. Now anhydrous means without water. Okay, nothing else. It means without water plus water. Okay, just to differentiate it from hydrated anhydrous. Okay, this is okay. Let's move on. Is the reaction exothermic or endothermic? Explain your answer. Now somebody else. Come on, Ahmad, Azam, Abdul Ahad. Come on. Read the question again. Okay, I'll give you a hint. Okay, read the question. The answer is in the question. When iron 2 sulfate crystals are heated in a test tube, they change to a white powder and condensation collects at the top of the tube. Now tell me.
Endothermic.
Ibrahim, did you raise your hand? Did I say okay? You can answer. But it's okay. Yes, you are right.
No.
It's endo. Yes, it's endo. Why? Because we need to give in heat. Yeah, no, exo means release of heat. Endo means like the energy is getting inside. Like you are. So whatever you are heating, whatever reaction needs heating is an endothermic reaction. Like your cooking, all the cooking is endothermic because we have to heat, right? So it's endothermic. Okay. Okay. What color are iron 2 sulfate crystals? Do you know the colors of the ions? Do you remember the colors of the ions? Huh? जोर से बोलो. जोर से. It's okay even if it's wrong, it's okay.
Are they gray?
Gray. Now remember, iron is a transition metal. Okay. Transition metal ions are really bright colored. Remember.
Yellow?
No. Who knows the color of iron 2? This is iron 2. Yes, Ahmad, very good. I'm happy. Yes, Ahmad, yes?
I think green.
Yes. Yes, iron 2 ions are green in color. Iron 3 ions are, well, by the way, it was there in some chapter, remember? Sundus, what chapter was it? Which gave the colors of all the ions? Okay, iron 2 are green in color. Last chapter, maybe that one. Last chapter, yeah. Iron 3 are reddish brown. Okay. And copper 2 plus are blue in color. Okay, what was the color of okay. Now chromium 3 plus, chromium 6 plus. Okay, they also have their color. I think chromium 3 plus is green, if I'm not mistaken. You should know these colors. Okay, you should know these colors. It's very helpful. They're very helpful. Cobalt 6 plus, I think, is pink in color. Okay, you should know these colors. Okay, keep memorizing them, especially in A levels. Especially in A levels, they are very, very important. Especially in practicals, when you will do practicals. Okay. Okay, when water is added to the white iron sulfate. So this is white. Anhydrous powder is white. This is pale green. Okay, these are hydrated crystals. This is pale green, and these are this is white powder. Now, when water is added to the white iron sulfate, that means water is added to this white thing, there is a hissing sound as steam is produced, and the iron sulfate changes back to its original color. So what's happening here? What's happening here? And yes, Ahmad, you want to tell me what's happening here? When water is added to the white iron sulfate, there is a hissing sound as a steam, and the iron sulfate changes back to its original color. Yes, Ibrahim, yes?
It absorbs the water, it rehydrates itself.
Yes, it has absorbed the water and...
It is exothermic, so it hisses. It's exothermic.
Very good, very good. Yes, and...
And
So this reaction is going backwards, right?
yes, ma'am.
Yeah, so that means this shows this reaction is reversible. Right? This reaction is reversible. So therefore
Yes.
it's, yeah, so the backward reaction. So if this is endothermic, the forward reaction was endothermic. That's why it needed heating, remember? You had to heat it. So the backward reactions would be exothermic. Okay, we haven't done reversible reactions, by the way. We will do, that's next. Okay. Now explain these observations. So yeah, you just explain, because we added water, because the reverse reaction is exothermic, energy is released instead of giving in, and that energy is converted into sound and thermal energy. Okay, and it, yeah, this equation shows, okay, now we will not do this. We will not do this because this is a reversible reaction. Yeah, we can. It's okay. This is easy. Now this equation shows a similar reaction. This is same, but this time the salt is different. Okay. What is the meaning of the symbol this? Easy. Yes. Yes, Aju. Hamza. Okay, Hamza.
It means it's a reversible reaction.
Yes, it means it's a reversible reaction, meaning forward and backward both can take place. Okay, explain how this reaction can be used as a test for water. Okay, Nabil. Yes. Okay, Sidra wants to try. Yes, Sidra.
So are they asking for this?
No. Explain how this reaction can be used as a test. This reaction. Well, by the way, this reaction can also be used as a test for water. Yeah. Okay, explain the top, but they are asking about this, but the same reasoning for
Okay,
both,
so
same reasoning.
Only if you add water will it turn into its original color.
No, only when you add water will it lose its color.
When water is added, it can produce and add the changes back to its color.
Yeah, original means like this is pale green, this is white powder, anhydrous is white, hydrated is blue. Okay, and hydrated here I think is pink. I don't know what the anhydrous color is. I'm forgetting what the anhydrous cobalt chloride.
So it will lose its color or take back its
Yeah, so you will say that only by the addition of water will this salt, I don't know what the color of this is, but whatever the color would be, find out what the color is, and that color would change into pink hydrated crystals.
So that means it will turn back into its original.
But don't use the word original, okay, because original is confusing. We don't know what original are you talking about. Is original this crystal or this hydrated crystal? So use the term hydrated and anhydrous, or use the term pink hydrated and you know, whatever the color is. You use the colors, either
Blue,
use colors.
teacher, blue.
Yeah, okay, blue. So from blue to pink. Okay, so when you add water, the blue powder will turn into pink crystals.
And that will only happen if you add water.
That will only happen if you add water. If you're using this as the test of water, then you will say that only by the addition of water will the
turn from white to blue.
Yeah, if this is white, yeah, this is white, right? Yeah, white powder. So the white powder will turn blue. By the way, this is also a pretty a good test for finding out if, oh sorry, ये blue नहीं है, ये green है. Yeah, pale green, sorry. This. Okay, nahi, but we have other green as well. Copper 2 plus is also, sorry, chromium 3 plus is also a green in solution. So yeah, so this is not a good test. You know why this is not a good test? Because we also have chromium. Chromium 3 plus also gives green. So you know, we don't want to confuse. So yeah, stick to this. This is the test for water. Okay. Okay. Is there any question? Is there any question so far regarding these? Regarding these, is there any question?
Over here, there's the same thing as the other side of it. It's like the exact same thing.
Yeah, Sidra's question is that aren't the two sides of the equations exactly the same? What's the difference? That's a very good question, you know. What's the difference? Can anybody answer? Sidra is asking, the two sides of the equation are exactly the same, then what's the difference? Where is the reaction going on? Yes, Ibrahim?
After the iron sulfate, there is a dot that means aqueous. I mean hydrated. I'm sorry, hydrated.
Yeah, okay.
The dot after FeSO4.
Okay.
That means it is full of water. It has water in it.
Okay. And this?
And this has a plus, so it means it doesn't have water.
Yeah. I don't know how exactly. You can Google search it, by the way. This is Google search the structure of hydrated iron 2 sulfate crystal. Google search it and find out. Iron 2 sulfate, but it is something like this. I'm just making a rough. Okay, the original might be different because this is an ionic compound, right? So this has 2 minus charge, this has 2 plus, right? And so that's why they are attracted to each other, because of the opposite charges. Now they are surrounded by 7 water molecules. Now how exactly, that you can Google search. Okay, I did not get time to prepare 1, 2, 3, 4, 5, 6, 7. I'm drawing 7. My diagram is very rough. Something like this, something like this. There will be regular arrangement of water molecules. Now, what are these dotted lines? Are they bonds? Well, they are bonds, but what sort of bonds are they? Yeah, exactly. Sidra is asking, are they intermolecular? Because remember, we have two types, inter and intra. Intermolecular and intramolecular. The inter means, sorry, inter means between, it means between. Intra means within the molecule. Now, if for example, these are water molecules, okay, these are water molecules. Now, these are between intra and inter. They are neither intra nor inter. They are stronger than inter, but weaker than intra. So these bonds are pretty, I mean, they are stronger than inter. So you will always have 7 water molecules attracted to 1 mole of iron 2 sulfate crystal all the time. The ratio is the same. Ratio will stay the same. That's why we write this equation. With 1 mole of iron 2 sulfate, you will have 7 moles of water surrounding it. 1 mole of cobalt chloride crystal, you will have 6 moles of water surrounding it. Okay, so this is a particular ratio. This is a specific ratio. It stays like that. Okay, and the shape of the crystal, the color of the crystal, everything is because of this ratio, because of this all, because of everything, this whole structure. If this structure breaks somehow for any reason, if for example 1 water molecule is lost, this whole structure will be destroyed and it will no longer give you the same crystal shape. It will no longer give you the, even the color might be affected, you know. So that is why this is a chemical reaction, but it is a reversible one, but it is a chemical reaction. And the difference is that here the 7 water molecules are bonded, okay, whereas in this case, in the case of product, they are separate. Iron sulfate is separate and water molecules are separate. They are no longer bonded to it. They are no longer surrounding it as they were before. Did you understand? So this is the difference. So now this is without the water molecules. That's why it's called anhydrous. Okay, and why do we call it crystal? Because it has a special shape and arrangement which gives it its shape.
So is this in solid?
Yes, this is in the solid state. Yes, this is also solid, by the way, anhydrous, but this is liquid, this is water, this is water. These are,
So these
just
are
trying to
now
make water
normally
molecules.
water molecules.
Yeah, these are normal water molecules now. Okay. Okay. Next question number 3. A student used the apparatus shown below to investigate the rate of reaction of calcium carbonate with dilute hydrochloric acid, and this is the equation. This is the setup. Okay, we have the conical flask on sitting on a weighing balance. Now the weighing balance will give us the readings of the mass of the of everything which is at the top, reactants and everything and the products. Now use the information in the equation to suggest why the mass of the flask and contents decreases with time. Now, you know, sometimes the answer to the question can be found within the question. Like they're saying, use the information in the equation. Now look at the equation. Now you have to find out the reason why the mass of the flask and contents decreases with time. Yes, Ajwa. Yes, Ajwa.
So in the equation, they have shown us that carbon dioxide is one of the products
Okay.
And since it is a gas, it can escape into the air through the
Okay.
cotton wool.
Yes. Okay, Abdul Ahad. Okay. And cotton wool, and see, we are not using any bung. We are not using any wooden cork or anything to block this. But this is a cotton wool, which is highly porous. And so vapors can easily escape. Sorry, the gas molecules can easily escape. Yeah, even the vapors, water vapors can escape. So that is why the mass of the flask and contents is decreasing, right? Now, the graph shows how the mass of the flask and its contents changes with time. So on the y-axis, we have the mass of flask and contents in grams, and on the y-axis, we have time in seconds. At what time was the reaction just complete? Yes, Ahmad? Ahmad,
600 seconds
how come? How
because
did you?
it's
Yes,
because
yes.
it's stable then because of the carbon dioxide is gone off and water also
No, but from the graph, how did you find out?
because the line is straight now.
Yes, so you will say that the graph has become straight. This means that the mass is of the whatever is in the flask is not decreasing anymore. So no matter how much the time passes, the contents are staying the same. Very good, good question. Sidra is asking why then we didn't say 700. The graph is flat even at 700. Okay, by the way, Sidra is a 6th grade student. I just forced her to stay with me in this class. So that's why she's asking. Can anybody answer her question? Why didn't we say 700? Yes, Ahmad? Yes, Nabil? Sidra is asking that why didn't we say 700? The graph is flat even at 700.
Because it started to become flat at 600 or 630.
Okay. And so the question is asking at what time was the reaction just complete? So yeah, even if you have 800, 900, now the graph is going to stay the same. The graph is going to stay flat. But the question is asking at what point did this happen? At what point did this start happening? So you will see where is the graph leaving the horizontal, okay? Because remember our y-axis is the mass of the flask and contents which are left behind, right? So the mass is now constant, okay? So that happened between 600 and 630 somewhere. Okay, on a copy of the graph, mark with an X the point where the speed or the rate of reaction was fastest. Ajwa, Akbar, yes, Hamza, come on, you guys, please participate. It's okay to be wrong. The more you guys will answer, the more I will know where you need help. Then I'll be able to help in a better way.
Teacher, above the
Yes.
100.1.
Okay. So how did you find that out? How are you saying that? Yes, your answer is correct. What did you say? 100.1?
Above than 100.1. Little bit above.
A little bit above 100.1.
Yes, yes.
Okay, why? What made you say
Because
that?
because curve is starting because
Yes. It's okay. It's okay. Even if you are wrong, it's okay. But see, they asked about the rate of reaction, right? What is the rate of reaction? Rate is the gradient of this graph. What is the gradient? How can we find out the rate of a reaction? Remember, I told you two things. Either you measure the mass of product per unit time. This is one way, mass of product produced per unit time. Remember, rate is always per unit time. This is one way of measuring the rate of a reaction. Another way is to measure the mass of reactant used up, or yeah, mass or concentration, whatever. Okay, or mass of reactant left behind can also be used, left behind per unit time. Both of them. So these are three ways of measuring the rate of reaction. Mass of reactant used up. Mass of reactant used up. If you do not, of course, measuring used up is difficult. What is left behind, measuring that is easier. So these are different three ways of measuring the rate of a reaction. So remember, what is gradient in math? What is gradient in math? Tell me. Who will tell me the formula for gradient? Come on, this is maths. Who is good at maths? How do you find out the gradient of a graph? Yes, Ajwa?
y1 minus y2 over x1 minus x2.
No, Ibrahim, I asked Ajwa. Yes, Ajwa?
y2 minus y1 divided by x2 minus x1.
Yes. Yeah. So what is this? y2 minus y1, meaning how much did the y-axis changed, the difference, divided by how much the x-axis changed. So change in y divided by the change in x, that's the gradient. Okay, something like this, right? This is how you find out the gradient, right? Now, how do we find this out? By drawing a tangent. Remember, we draw a tangent to the graph to find the gradient at that point. At that point. Now, tangent, what is a tangent? Tangent is a line, straight line that touches a circle at a point perpendicular to its radius. Tangent is a line that touches a circle, and that line should be perpendicular to the radius of the circle. Okay, so easy. Now you don't have to go into the details of them. You don't have to do exact math here, because this is not math, this is chemistry. An easy way of doing it, but I am telling you all of this so that you understand why we are doing it this way. Okay, so what I will do is I will take a ruler and I will see where is the ruler, the slope, where is the slope the steepest. So look at this, at this point. So I am making the ruler touch the graph at one point while making sure that it is roughly perpendicular to, if there was a radius, that it should be perpendicular to it. So this is the slope at this point. Okay, now if I want to find out the gradient at this point, can you see the slope is like this? Can you see this is now less steep as compared to this? This is steeper, right? Can you see this slope is steeper as compared to this? Now, if I want to find out the gradient at this point, again, my line should be touching this. And so can you see the slope is now even more gentle? So much so that here the gradient is absolutely zero. When the gradient is parallel to x-axis, that means the gradient is zero. Why? Because the y change is zero. In this case, y2 minus y1 is zero. So gradient is zero. So can you see the slope is changing like this? Like this. So लेट गया, पहले थोड़ा सा खड़ा हुआ था, फिर ये लेट गया, फिर ये बिल्कुल ही लेट गया, फिर ये सो गया, right? So where it is steepest, that's where the rate of reaction is the fastest. Why? Because that means mass of the, so that means more, yes. Yes, so that means more of the reactant is used up divided by time. So this is more. rate of reaction here is more. Okay, here it is the fastest. So at this point, I will say at this point, where the tangent is touching the graph. Okay, so tangent is touching the graph here. 100.3, between 100.3 and 100.4. Yeah, this would be 100.35, something like that. Okay. Any question regarding this?
Miss, I have a question.
Yes.
Miss, near 100 down there, it's the graph of the y-axis breaks. What does that mean?
What? Sorry, what?
Under 100, there in the on the y-axis line, there is a slant curve, or this line is a triangle, small. So what does this mean?
I don't know. I did not understand your question. Did you understand? Can you please speak a bit louder? I'm so sorry. Ibrahim, can you please be quiet? Yes.
Miss, on the y-axis, under 100, there is a small curve type thing. What
Oh, okay. Oh, you're asking about this?
Yes.
Oh, okay. Very good question. Very good. Nabil, I like this question. Yes. नहीं ये लगाने की जरूरत नहीं ये नहीं लगा. Okay. This means that the graph is broken here. Now, why did they do this? Why did they do this? But because can you see that they have started from 0, but they have suddenly come to 100. Okay, they missed all these 10, 20, 30, or so on and so forth. So this shows that the whole graph, they have skipped that part. Can you see now it's 100.1, 100.2, 100.3, 100.4. Okay, now they are in one big square. This one big square, this one thing stands for 0.1. The whole thing stands for 0.1 because it's increasing by 0.1. By the way, this is math. This is not chemistry. Drawing graphs, this is part of math. Okay, by now you should be familiar with making and drawing and understanding graphs. So this broken line means that this scale is not continuous. This y-axis, and can you see the broken line is only on the y-axis. They did not break the x-axis line. Why? Because it is according to scale. It is continuous. Okay, so 0, so on the x-axis, one big square stands for 100. One big square stands for 100 seconds. 100 seconds, another 100 seconds, another 100 seconds, another 100 seconds, and so on and so on. But here you can see that from 0 all the way till 100, they have skipped all those numbers from 0 all the way till 100. And now they have started counting by 0.1, 0.2, 0.3, 0.4. Now, why did they do this? See, it depends, the scaling of your graph depends upon what sort of values do you have. So maybe their values were increasing only by point. So because their values were only increasing by point, therefore, and they did not have anything below 100, okay, and they knew that they are not going to need those values below 100. So they, and the rest of the graph is according to some scale, whatever they have chosen. So that's why it was easy. So broken, so you can also do that. You can also do that, but then you will also have to use a zigzag. This is called the zigzag line. It shows that your y-axis is broken. Okay, you have omitted some parts. You have omitted some parts from the y-axis. I hope I made some sense. Okay. Did you understand, Nabil?
Yes, Miss. Thank you.
Okay. 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 The student repeated the experiment but altered the concentration of the hydrochloric acid so that it was half the original value. In both experiments, calcium carbonate was in excess and all other conditions were kept the same. On a copy of the graph, draw a curve to show how the mass of the flask and contents changes with time when hydrochloric acid of half the concentration was used. Yes? Anybody wants to attempt answering this question? Yes? Come on. So what are they doing? Now look at the equation. This is the equation. Okay. Why did they say that calcium carbonate is in excess? What does that mean? They said that calcium carbonate was in excess. What did this mean? What does excess means? Yes, Ajwa?
More than required.
Very good. So why did they mention it here? Does it affect our answer? Yes, Ajwa? Come on. Have I done this? Have I done excess and limiting factor here? Okay. Was in excess. What does that mean? That it is in excess. Okay, I'll tell you. Right now, I'm gonna just tell you briefly. Okay, but otherwise, we need to study this in detail. Now, excess means that no need to worry about it. This was in excess more than required, so it won't affect the rate of a reaction. I remember talking about this. I think I have talked about it in my previous classes. No, I think I have. Yes, I have. Now I remember. Okay, so calcium carbonate is in excess in both the reactions, in the reaction, the graph of which is drawn already, and in the new reaction in which the concentration of hydrochloric acid has been halved. Right, in both the calcium carbonate is in excess. That means no need to worry about calcium carbonate, just concentrate on hydrochloric acid. So in one equation, hydrochloric acid is, the concentration, whatever it is. And in this other experiment, the concentration of hydrochloric acid is half. So now, how will the graph of the reaction be affected? Come on. Whatever you know, please tell me. It's okay. So rate of reaction we have done, right? The effect of concentration on the rate of reaction. Yes, the concentration, you are decreasing, you are halvening it. Yes, Ajwa? Very good.
So when we have the concentration, that means the rate of reaction decreases,
Very
and
good.
the
Yes.
slope of the graph, it will be less steeper,
Yes, very good.
and it
Yes.
will be above the original slope.
Very good. Yes. Yes. See, half the concentration, meaning half the molecules per unit volume. Whatever the number of molecules was initially, now half of that. Okay, so if you had 4 molecules, now you have only 2, to keep it simple, right? So of course, less collisions, less product formed, and therefore the rate of reaction, which is the mass of product formed, or the amount of product per unit time, would also be halved. Rate of reaction will also decrease by half. So half of everything, but the starting point would be the same. Starting point would be the same. Yeah, okay. If the total volume of the total volume of hydrochloric acid is the same and only concentration is happened, then the starting point will be the same, but everything else would be happened. So if this is almost 100, I mean from here till here, right? So it's come midpoint till here, midpoint. So I will make a graph like this, and I will and even at this point it won't complete. Okay, the reaction would take longer to complete because it's slower. Okay, so remember, so make sure that your graph is not leveling out. You know, like make sure that your graph is not leveling out here. It should be on a downward slope. Like this, something like this. So it will still, it has not leveled off. It should not level off. Are you getting me? Why? Because we don't want the two reactions, or maybe it can, you know, because this ended here at 600. So this should end somewhere farther away. It should level out a little later. Yeah, by, you know, at 800 or something, because this is a slower reaction. Okay, because you decrease the concentration of hydrochloric acid by half. Okay, okay, let's move on. Is there any question regarding this? Am I missing any point? Okay. How does the speed rate of this reaction change when the temperature is increased? That is easy. Again, same thing. They will have greater average kinetic energy, greater than the activation energy, and so on. And so, you know, I'm moving on. Smaller pieces of calcium carbonate are used. Okay, who will tell me what will this do? Smaller pieces of calcium carbonate. Yes, Ibrahim?
The surface area is increased, so
Very
the
good.
rate of reaction speeds up.
Yes, talk a little about, you know, exposure between the reactant molecules. Talk a little about that.
Yes.
Yes.
Okay. When the surface area is increased, so the particles are exposed, more are exposed to the
Yes.
substance, so the reaction is increased. Rate of reaction is
The
increased.
smaller the pieces will be, more molecules will be exposed to the reactant. Bigger pieces would mean that many molecules will be deep inside the lung, because only the surface molecules are getting the chance. Okay. Now, I know time is up, but a little, I want to talk about the limiting and excess. When they say excess, just a little, I will not take long. I will try to, okay. For example, you have sandwiches to make, okay? Sandwiches. I'm giving you an example of a sandwich. Or let's talk about bun kebab, okay? Okay. So, for example, my reaction is this. Bun, this is a bun, plus, let's say, what should I say? Okay, kebab. Okay, this is a kebab. And I am getting a bun kebab. Bun kebab looks something like this, right? Okay, these are the bread pieces, and this is the kebab, right? So this is bun kebab. This is my chemical equation. This is my reaction. Okay. Now I am saying that bun is in excess. Bun is in excess. Why? Because I have, let's suppose, I have 5 buns. Let's suppose 6 buns. I have a lot of buns, but I have very less kebab. I have very less kebab. For example, let's say I have 3 kebabs. Okay, I am shading the kebabs. Okay, so that you can differentiate. Okay, these are the buns, these are kebabs. Now, how many bun kebabs can I make out of this? Who will answer me? How many bun kebabs can I make? Full bun kebabs. Yes, Zen. Yes, Zen.
3.
3. Why?
Ma'am, because in 2 bun kebabs in 2 buns there will be 1 kebab.
Right. Right. In 2 buns there will be 1. Okay, and remember, this is, you know, before cutting. I will cut this and I will make the 2. Okay, so don't count these as 2 separate. Okay, don't confuse. Just take, this is 1. Okay, 1 bun, 1 kebab. That's it. Okay, so 1 kebab with 1 bun, 1 kebab with 1 bun, 1 kebab with 1 bun. So I will have 3. I will have 3. Okay, I have 3 bun kebabs. So this is an excess because I did not use these 3. So this was an excess. I did not use these 3. I only used these 3. And this is the limiting factor. This is my limiting factor. Now, the thing is, if somebody asks me in this reaction, what decided the number of buns? Did kebab decide the number of buns, or did the buns decide the number of bun kebabs?
Kebab.
Very good. The number of kebab decided the number of the, so that means it is always the limiting factor which decides the rate of a reaction. It is always the limiting factor that decides how much product will you have, not the one that is in excess. That's why when in the question it said that carbonate is in excess, I said it just means don't worry about it. Remember, when they said calcium carbonate is in excess, I said don't worry about it, because that means we have more than what is required. So it won't affect the final product. Do you understand? But this was limiting. This was limiting because they happened it. So this will decide what the rate of reaction is. You understand? So this is what they mean by limiting factor and excess. Remember that this is very easy. Okay, I hope you understand with this analogy now. Okay, so it is always the limiting factor. So that's all I wanted to say. Is there any question? Please, you're most welcome to ask. Any question? Come on, guys, ask some questions. Okay, then I will now end the class. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh, and physics class day after tomorrow. Okay. Assalamu alaikum.
Walaikum assalam.
Allah Hafiz.
Allah Hafiz.
Hafiz, miss.
Allah Hafiz.